Welcome to lecture 52. This is on various data types and their characteristics. So in this lecture, I will explain what are the different data types, formats which could be used in the GIS and what is their special characteristics in terms of the GIS software. So let us begin with this lecture. As you have learned in the previous lecture that geographic data is one of the important component of GIS. So this geographic data will come from the different sources, and in GIS we can represent this data in three forms. So it could be a point feature, it could be a line feature, it could be a polygon feature. So when we are showing in the form of a graphical map any features on the ground surface, natural feature or man-made or cultural features, we are showing in any one of these three entities, either point or line or the polygon feature, and these three are different to a GIS software. So let us see the characteristics of these three. I am showing you the administrative unit boundary, and within the boundary there are different dots. So these dots are showing the point feature. There are some dots with the blue color and some dots are there with the red color. So these are indicating that there are two kinds of features which are present in my area, and I am showing those features at just dot, although it will depend upon my working scale. Many times if I am working at a very small scale, then the big feature I can show as a dot. If I am working at a large scale, then even the dot becomes the area feature. So it depends on the scale, working scale on which we are working. But normally if I am showing house, hospital location, location of the school, location of the post office, location of the telephone poles, well, or police stations, I am showing all them by dots. So dot is indicating that this is the location, this is the geographical location of that particular point. So in the spatial maps, the different colors here are indicating the different features and their correct location in the area. The second type of features are line features. So linear features could be road, footpath, river, railway line, canal, pipeline, cable, transmission line. So any of those features which are linearly represented, I can show them in the form of a line on my map. So here in the map itself, here now you can see that there are features which are shown by the red lines. So these are all different kind of roads, and there is a feature which is shown by the blue, which is the water body feature. It's a river which is flowing through the area. So these line features are shown by sometimes the single line and sometimes by the double line also. Polygon features, this is the third category. So there are many features which are showing by the polygon. Administrative boundary, for example, if there is a big lake, we are showing the outer boundary of the lake. If there is a big building at the forest region, there is a reservoir area. So these are all we are showing by a polygon. So we are closing that figure. So you can see lots of polygons are shown within this administrative building, and these polygons could represent maybe the village boundary within the administrative boundary itself. So each of this polygon now has its own entity. So these are the three different type of features which can be shown in the GIS. If we look at the geometry of these three types of figures, they are the defined in terms of the vertices. When we are creating these features, so they are described in terms of the vertices. The point geometries are made of a single vertex. If I want to show the point data, then just a single vertex will show me the point, and single vertex means that x and y coordinate of that particular location now is known, is created. Then if I am creating line geometrics, then line geometrics would be represented by two or more vertices. So minimum 2 vertices are required in order to draw a line. So maybe I have one point here and one point there. So x1, y1 is the coordinate of point 1 and x2, y2 is the coordinate of point 2. If I join this together, then I have the coordinates like x1, y1 and then x followed by x2, y2. So if I have that kind of a coordinate system, so this is representing a line. And we are talking about the polygon geometries. In the polygon geometries, this is basically the connecting lines together. So we have at least 3 vertices are required in order to make a closed area. And if I take the 3 vertices, then x1, y1, x2, y2, x3, y3, and also again I will have x1, y1. It indicates that my starting point and the end point, they are same and they have the same coordinate. So this is like a polygon, it is like a closed figure. So if I have a single coordinate system like x and y in my attribute table, it is indicating the point. If I have a string x1, y1 and x2, y2, things like that, this is like a x3, y3 and so on. This is like a line feature. But if I have x1, y1, x2, y2, x3, y3 and so on, and last point is same as the starting point x1, y1, this indicates the polygon feature. So I am representing the graphical information now in the form of the attribute table, and which has a coordinate system attached to these spatial data. Now, there are different uses which I can make of this geographical data. I can use it for analysis purpose. So, there are certain operations I can carry out those operations. I can turn this data into very useful information. Then I can carry out the measurements from this data. So, a measurement of means the length of the line. So, suppose there is a line feature, I wanted to know the length of a line or the partly length of the line, that I can get from this data. If I want to know the area of a polygon, the perimeter of a closed polygon, we can carry out that kind of a measurements very easily with the help of these coordinate systems. Then we can have attribute queries from this geographic data. We can carry out proximity analysis, we can carry out overlay analysis, or we can create the model of the surfaces and networks. So this all we will learn in our subsequent lecture once we have understood the characteristics of the geographical data, how to use them for spatial analysis. Now, there are 2 broad formats of the data sets. So, you can see here there is one format which is called vector format, another format is called the raster format. So, we are showing you a real world, and in the real world there is a stream which is flowing through the area, river. There are 2 houses and there are trees, cluster of trees there. So, we have a point feature in the form of the houses, we have line feature in the form of the river, and we have the polygon feature in the form of the forest area, cluster of trees are there. Now, if I have to represent this, I have to create a map of the real world data. I can have a vector representation and I can have the raster representation. So, there are 2 kind of data formats, 2 kind of GIS supporting software available. So, in the vector representation, you can see the vector has a magnitude and a direction. So, you just keep on digitizing this particular feature, and you can see the point feature is shown here by a single dot. Then this is a line feature which is representing basically the river. The entire width of the river is shown by the line, single line. So, we can draw in the center somewhere this particular line which is showing the river feature. Then there are a cluster of trees which are shown by the polygon features here. So, in terms of the coordinates, it has x and y coordinate attached, the point feature. The line feature will have x1, y1, x2, y2, x3, y3 and so on, and the polygon feature will have x1, y1, x2, y2, x3, y3, x4, y4 and so on, and the last point will be x1, y1. When we want to represent this entire data set, vector data set into the raster representation. So what do we mean by raster? Is it the grid cell based representation of the same data? So if I superimpose, let us say, a grid of uniform cell size. So here a 10 by 10 grid is shown and the entire data is divided into 10 by 10 matrix. So I am dividing into 10 grid cells, 10 by 10 grid cells, and under each grid cell now there will be either any feature present or no feature present. As you can see here now, the house is present in the cell number 2, 1. 2 is the line number and 1 is the row number here. Similarly, the other house is present in the line number 6 and row number 7. So, in these two grids, the house, the point feature is lying. Now, the river feature is lying into several grids. So, these are the grids where R is written, these are the grids where the river is flowing. T, trees. So, there are 4 grids where tree is falling. So, this is making a polygon here, and there are 2 grid cells which are covering the cluster of trees, other cluster of trees. So, one can see from this particular figure that other cells have no feature present. So, they are blank. There is no coding which has been done for these cells. So, in the entire matrix now, in each grid cell, either the feature is present or no feature is present, but every cell has a coordinate system. So, I can locate each cell now by its coordinate systems of the grid cell coordinates and locate a particular feature in the form of the grid cell. Now, a polygon which was a polygon with a more or less true shape on the ground, now it has become a kind of a 2 by 2 matrix which is a grid. So, it is slightly a distorted kind of a figure which I am getting from the raster data set. We will understand more in the subsequent example here. So, broadly now there are 2 kind of a data types, vector data, raster data. So, as you can see, the point feature will occupy minimum 1 cell. So, this point may lie anywhere within the cell. If it is lying in even in the at the corner of the grid, the entire grid will be taken as occupied by that point feature. So, similarly the line feature. So, although it is a very thin line and the width of the line is much smaller than the width of the cell, but the entire grid cell is considered to be occupied by that particular line. Similarly, the polygon feature will have the group of cells together. So, it depends upon the grid cell size, that how many grid cells are occupied by a particular feature will be determined by the grid size. So, in order to understand, this is the real world data, ground data, actual ground data, and this is the vector representation of the ground where we are representing the water feature, a pond in the center, and then there are rivers and there is a forested area, and the same representation in the form of the grid cell, that is called the raster format. So, this grid cell is to be user defined. We can define the grid cell, we can make a smaller grid size, we can make a bigger grid size. It depends upon the total area and the homogeneity of the feature, the type, what type of features are present in the area. So, one can see that now the figure become blocky. So, the actual shape which I was able to recognize and compare 1 to 1 in my vector data with the ground data, now it has become little difficult when I am having the same information in the form of the raster. It has become a blocky figure. So, it looks like that river is flowing a zigzag, although the river is not flowing in that zigzag as I had shown on the raster data types. So, again a vector representation of the data point feature, the line feature, and this is the area feature. So when I represent in the form of the vector, the polygon will look like very smooth polygon, the line will look like a straight line to me. But if I show you the same data now in the form of the raster representation, you will find that this data has become blocky kind of information. So stepped data, it is occupying blocks by blocks. So now the water features are shown here with the blue color, that linear feature is shown by the brown color here, and the point features, they are shown by the light brown color. So completely the shape has changed. Now if I want to carry out the area measurement of the pond or the length measurement of the line, I may not get the correct measurement from this. So vector data will actually allow me to carry out the measurements very accurately, retain the shape of the feature. But here in the raster representation, I may have only the blocky kind of a information, and we can get very rough idea about that particular feature. So I am superimposing the two now, so that you understand. And when you have the raster data, like satellite image is in the raster format, or if you scan some paper maps, that become the raster maps. So once you have the raster information, and suppose you want to convert back to the vector information, because you feel that the vector information is much more accurate representation of the ground features on the earth, then there are algorithms available, raster to vector conversion algorithm, and these algorithms basically some of the algorithms will take center of the each grid, and that is how you can convert back. But it is not preferred, because many of the software will actually give you distorted shape. You will not get the exact shape as the vector original data is there. So you will always get the distorted shape because it is based on certain mathematical formulation. So normally what we do is, when we want to work with the vector data, we create the vector data. We don't convert raster data into vector data using some kind of a algorithm, because we get some kind of a misleading shape and size and dimension. So there are now two issues, rasterization and vectorization. Now regarding of the input device, now it is necessary that if the final product MI is in the raster format or the vector format, like image, if you are classifying and creating a land use and land cover map, this is the raster output. But if I am digitizing a certain information, that become the vector information. Most of the GIS programs which I have mentioned before in my lecture, they have the capability to convert one form into the another form. But there is a problem when you are converting raster data back to vector. Vector to raster can be done. So grid side cell is very important when we are looking at both the data sets. So in the vector data sets, because you can see very smooth line, you can see the straight line between the 2 points, which becomes blocky. So how to avoid that blocky kind of look? You can have a smaller grid size. So if you change the grid size from larger to the smaller, probably you can retain the shape. You can maintain the shape, you can identify the feature, and you can maintain the measurements also. But you have to go for a very small size. Now the fear is, now the disadvantage is that once you have a smaller grid size, then the storage capacity, you require a huge storage of the data, because the same data now requires a big storage when you are changing the grid size from the larger grid size to the smaller grid size. So that is also the advantage and disadvantage. Now there are spline algorithms available, smoothing functions available to vector lines. There are several software available, as I told you, R2V, raster to vector conversion, or ArcScan and ArcInfo. These are some of the software which are available, can convert raster data into vector data. Now coming back to vector data, now we have in the vector data we have the data which has geometry to it, attached to it in terms of the point, line and polygons, and the second type is in the database is the attribute data. So for each of these features there will be attribute data created by the software itself, and these three types of data will be dealt differently, and we can combine them together also using some kind of a spatial analysis tools. So when we are dealing with the vector data, although it is maintaining the shape and you can recognize the feature and your measurements are very accurate with the data, it requires the topology. So this is a new term now. What is the topology? So it's numeric data which is created, and this numeric data will describe the adjacency, containment and connectivity. These three things one has to establish by creating the topology. So that means if there is a feature adjacent to this, what are the other features? That is the relationship. Containment, if there is one polygon and there is another polygon within that big polygon, then one polygon is contained within the other polygon. Then connectivity. So if there is a road network, there is a connectivity between one road length to the other road length. So that connectivity has to be established. So these three relationship has to be established in the vector data. Adjacency, is there any adjacency? What is the adjacent polygon to polygon A, right? And what is contained within a particular region, and what is connecting a particular line or a particular feature. So this in order to understand this, we have to create the topology, and it is nothing but a set of rules which will describe how the objects are related to each other, how one object is related to the other surrounding objects, and higher level objects will have the high spatial topological rules also. Now this topology is very important, and if you create the topology, then overlay analysis, which is a very important functionality of the GIS, one can do. We can overlay, superimpose one feature over the other feature. So topology will allow many GIS operations to be done without accessing the point file. So you can establish the relationship, connections between the points with the help of this topological information. Now this is the example of the adjacency. So we have one land parcel which is shown by the yellow color here, and what is adjacent to this land parcel. If I like to know this from my database, then the green parcel here is the adjacent parcel. So I would have the information about this particular parcel which is just adjacent to that. Similarly, I have a soil type, and what is adjacent to that particular soil type, what object is present, that information I can get from the adjacency example once I create the topology. Then containment. So containment will give me, or coincidence will give me, one boundary can lie on the top of the another boundary. So I have for example, the blue one is the coastline, and there is a county boundary. So these two boundaries can lie on the top of the one another, or you can identify the bus routes on the top of the roads. So this is the bus route, but there is a road also. So both are superimposing, contained over each other. So this is what is required in many applications when you are superimposing one feature with the other feature. Then the third example is the connectivity. This is very important whenever we are talking of some network. So whether it is a drainage network, or it is a pipe flow network, or it is a road network, or the railway line network. So any problem with the flow from one place to another will actually have this networking issue. So connectivity issue is very important. What is connected to a particular feature in the surrounding, so that can be identified with this connectivity. So the topology will actually give me some kind of a query system I can develop, like what is connected to, what is within the given region, what is adjacent to a particular area, what is the north of a particular feature. So we can get actually these kind of answers from my data sets once I create the vector topology of the data. Now if you see the graphical information, that there is a, once I create the vector data, I have the node topology, which is the basically the starting and the end point of a particular line. Then I have the link topology and I have the polygon topology. So node topology is created when you are creating the point feature. Link topology is basically linking the several points on the line, and the polygon topology is when you are digitizing a particular polygon, then you are creating. So that information, so each of that node and vertexes which are created when you are digitizing these particular feature are very, very important. So topological data structures will dominate the GIS software, and you can also allow the error detection. You can also get the error detection and you can eliminate it. Once you create the topology, you come to know if there is any error present in your data set. Now there are certain kinds of errors could be there when you are creating the data set, vectorizing the data sets, like you have the undershoots or the overshoots error. So one can see that here is the undershoot. When I am digitizing a line and I am digitizing the connecting line, then both lines do not join together, but there is a small gap left. So this is called undershoot. While in other case, this is called overshoot, which is shown at the 2. The line overruns over the other line while it should have been stopped at the junction point. So if there is a undershoot kind of a problem, is the overshoot kind of a problem, this you will come to know when you are creating the topology of the area. The third kind of a problem could be sliver polygons. These are the sliver polygons are created at the common boundary of the two features. So there is one feature on the left, another feature on the right, and there is a common boundary between the two. And if you are digitizing that common boundary, then you twice, then chances are that you create these sliver polygons. Although it is small polygon, but it is an error. So let us see the vector data structure. So in the vector data structure, there is a point feature which is created by the node. Then there is a line feature here which is created by the starting node and the end node, and in between are the vertices. And there are polygon features now which are created by the node and the vertices. But the care which has to be taken while creating this kind of a data set is that the line which is common, this line is common between 33 and 39, it is not to be digitized twice. It is to be digitized only once. So in terms of the attribute table, if you look at the attribute table, then we have x and y coordinates for the point feature, we have the string of the coordinates for the line features, and we have for 33 polygon we have a closed loop kind of a coordinate systems, and for 39 polygon we have the closed line. So the line which is common to both the, it has been digitized only once. So if we again try to understand the node point and the vertices point in between, and then there is a node point which is actually at the starting point and the end point of a line. So we have a table like this where we have 4 points which are digitized Q, R and S and T, and their coordinate systems. When we are digitizing a line and creating the line, this is the starting and this is the end 4. So we have 1, 4, 2, which is the begin of the node, the end of the node, which is representing line 1, 1 and line 1, 2. So each line is represented by the beginning of the node and end of the node. And in between, you see, you can have the left polygon or the right polygon kind of a features. When we are digitizing the entire polygon, there are two polygons here in the shown in the figure, polygon A, polygon B, and it consists of the lines. So it is showing you that line number 11, 12, line number 52, 53 and 54 is making the polygon A. So this kind of a information which is created in the table is called the topological information. Now further, if we see in more detail the topology of the nodes which is created, because there are several nodes here starting N1, N2 and N3 and N4. These are the node points are the starting and the end point of a line when we are digitizing. In between are the vertices. So there is a statistics of the node here that it is linking the length L1, L2 or L3. So this is what is shown in this node topology table. In the polygon topology table again, there are several polygons which are shown here, A, B, C, and the bigger one is the D polygon here. So all that linking nodes are shown in the table in the polygon. Then link topology and the link coordinates are also created. So I have, for example, the L1 link in this particular figure. So there is a coordinate for that L1 link. So all the coordinates are listed. So every detailed information is created through this topology, and this information is useful not only to carry out the measurements but to carry out certain operations, the spatial analysis, to make the query from this database. So all that information is very important. So when we are creating the database, then it is important that we create the topology of the vector data. So if we now see the advantage and disadvantage of the vector data, it's a good representation of the ground reality. We can get the correct shape and size and orientation. It's a compact data structure, as you can see from the topological table. Topology can be described in a network and it shows the accurate graphics. The disadvantage is the complex data structure when you are superimposing several maps together. This simulation is difficult and some spatial analysis is also difficult, because in a grid based system you are picking the each pixel and carry out the pixel by pixel analysis. So this is a raster grid data structure is there, where the entire area has been divided into the smaller grid, and each grid has its geographical location in terms of the x and y, and also one attribute attached to that particular grid, what information is shown within that particular grid. So that is also there. Now it could be a continuous data or it could be a discrete data. There are both types of informations are required for different applications when we are dealing with the raster data. So this is a continuous data. When we have some kind of a information like elevation data or temperature data, we are showing that's a continuous data which we are showing. Now advantages and disadvantage of the raster data would be that it is a very simple data structure, because each of the cell can be defined by its coordinate systems. The overlay is easy because the one coordinate, one pixel will exactly overlay over the other pixel. Various kinds of spatial analysis are actually very easy to carry out. This is the uniform shape and size. Each of the file has a very defined shape and size. This is very fast to carry out the interpretation. Then the most disadvantage is that the information is very generalized, you get blocky information. It's very difficult actually to carry out the measurements from this, and projection transformation is difficult. So these are some of the merits and demerits of the both type of data products together. Now when we are talking of the file format, there are different file formats which are supported by the GIS software in vector format, and there are different formats which are supported by the raster format. So there are two types of file formats which are supported nowadays by the GIS software. Now you can carry out very accurate measurements from the vector data. If you have to carry out length, perimeter and area measurement from the raster data, you will get only the approximate, and the accuracy will depend upon the size of the grid which has been selected for that. So, this vector data we are using mainly to represent the real world feature into the GIS, and if we want to show the correct geometry of the point, line and feature, then we are using the vector data. And most of the GIS, when we are carrying out some spatial analysis, this is a little a complex process. You can create vector data by digitizing a lot of paper maps, by scanning them and digitizing it. You can create that kind of a data. The topology will show us the relationships with the neighboring features, and topology will give us some of the flexibility topological tools which could be used not only to carry out the measurements but to carry out some kind of a spatial analysis also. And in network analysis, the topology is very important for detecting the error present in the data sets. This is also important. When we are talking of the raster data, the structure is dependent upon the size of the grid cells, and raster data is good for when we are showing the continually varying information. So, this is good, and its spatial resolution is determined by the size of the pixel which we are selecting. It requires a large amount of the storage space, because even if those cells which do not have any information, that will be stored in the database. So, this is all about the data products. Thank you.